So shouldn't a parametric equation also have a tangent line? So this is a curve defined by a parametric equation. You could see that, yeah, there should be a tangent line there. And if you remember, if the curve was defined by a graph where y is a function of x, we can say the slope of the tangent line is the same thing as the derivative, or dy over dx. But how do we do this when we have parametrized curves where your x-coordinate is defined by a function of time and your y-coordinate is defined by a different function of time? Well, it turns out if your x-coordinate is defined by a function of time, you can take the derivative of it with respect to time. And if your y-coordinate is defined by a function of time, you can take the derivative of it as a function of time. And there's something called a chain rule here, that if you take the derivative of your y-coordinate with respect to time, that's the same thing as taking the derivative of your y-coordinate with respect to x times the derivative of the inside function, the x-coordinate with respect to time. Now, you could mathematically, as long as this derivative of the inside is not equal to 0, you could divide this expression into both sides of the equation, and you get a formula that tells you that the slope of the tangent line, that is the change of y over the change of x, is the same thing as the rate of change for the y-coordinate divided by the corresponding rate change of the x-coordinate. The only caveat is you cannot divide by 0. In terms of computation, it's pretty straightforward. Let's take a look at this parametrized curve and see if we can find a tangent line when t equals 1. Right here we have a graph of what that curve would actually look like, and actually the tangent line at the point when t equals 1 is right over here. But to find the equation for the tangent line, first we have to find the slope of the tangent line, which means we have to figure out whatever dy dx is. With a parametric equation, that means you're computing your dy dt and your dx dt. Sort of how quickly the y-coordinate is changing and the x-coordinate is changing with respect to the parameter t, which we usually think of as time. We use the regular derivative rules for the derivative of each of the coordinates, so chain rule for the y-coordinate, and a combination of the sum rule and chain rule for the x-coordinate. This is, of course, a complex fraction. You have to deal with complex fraction rules when you're evaluating this expression, but it's actually not too bad in this case. If we want to find the slope of the tangent line when t equals 1, we can now plug in 1 into our derivative function over here. So the slope of the tangent line is just 4. So you move over 1 unit in the x direction, you should move up 4 units in the y direction. To find the equation of the tangent line, we have to find a point on the tangent line. Evaluating the expressions for the x of 1 and y of 1 in our corresponding coordinate equations, we get this as the point on the tangent line, and then the equation of the tangent line is the regular form of equation, which is slope times the change of x from a point on the tangent line plus the y-coordinate of the corresponding point on the tangent line. Thus, the graph we see here.